Hello everyone, welcome to the lecture. Today's topic is circle diagram of an induction motor. Till now we study no load test of an induction motor and short circuit test of an induction motor. No load test is basically used to find out the core losses of an induction motor, and the short circuit test, which we also called a block rotor test, it used to find out the copper losses of an induction motor. Now the circle diagram of an induction motor is very useful to study its performance under all operating conditions. The construction of circle diagram is based on the approximate equivalent circuit. It is a diagrammatic representation of the performance of the induction motor. The circle diagram provides the information about the power output, losses, and the efficiency of the induction motor. The data which we use to calculate from the induction motor cycle diagram, the result which we obtained is the input power, rotational losses, stator copper losses, rotor copper losses, output power, output torque, starting torque, slip, speed, efficiency, and power factor. These all are we can calculate from the circle diagram. To draw a circle diagram, we took the data from the no load test and the short circuit test. This construction we divided into a few steps. Step 1, we took the I0 and Phi0 from the no load test of an induction motor, and in step 2, ISN and Phi S. Now I draw one circle diagram. Here we draw the axis OE and OX, which are both are perpendicular to each other. Then we draw OO dash. OO dash is nothing but a I0, which is we calculate from the no load test of an induction motor, and it is at an angle of phi 0. This is the phi 0. Now when we find out the O dash, then we draw a parallel line to the OX, which is just like this parallel line, and we draw the line OA, which is at the angle of phi S. It is the ISN, and OA represents ISN, which is IS V by Vs, and vector O dash A represents rotor current I2 dash as a reference to stator. Now it clearly says that A and O dash both are lies on the circle. Now we charting this O dash A, we charting this and find out the point C. This C is the center of the circle. This C is the center of the circle. We bisect the O dash A, and by this bisection we got the point C. It is the center of the circle. By this we draw a circle. And the point O dash and A lies on the circle, and we find the point D. The O dash D is the diameter of the circle. As the matter of practical contingency, it is recommended that the scale of the current vector it should be so chosen that the diameter is more than 25 centimeter in order that the performance data of the motor may be read with reasonable accuracy from the circle diagram with center C and the radius CO dash. The line O dash A, the line O dash A is the output line of the motor, is the output line of the motor. It should be noted that the voltage vector is drawn vertically. All vertical distances represent the active or power or energy component of the current. Now for the step 3, torque line. This is the torque line O dash E. The torque line, this is a line which separates the stator and the rotor copper losses. When we see that it is a line, the torque line, the upper part is the rotor copper losses and the lower part is the stator copper losses. When the rotor is locked, all the power supplied to the motor goes to meet core losses and copper losses in the stator and rotor winding. The power input is proportional to AG. The power input is proportional to the AG. The point E is such that AE upon EF is equal to rotor copper losses divided by stator copper losses, where O dash E is known as torque line. Now, how to locate point E? The question again arises, how to locate point E? Now, we have two types of rotor. One is squirrel cage rotor and the another is wound rotor. Now, for the squirrel cage rotor, rotor resistance per phase, that is R1, is found from stator resistance test. Now, the short circuit motor input WS is approximately equal to motor copper losses. Now here we neglecting our iron losses. Now stator copper losses is equal to 3 Ia square R1. Therefore rotor copper losses is equal to WS minus 3 Ia square R1. Therefore A upon EF is equal to WS minus 3 Ia square R1 divided by 3 I square R1. Now for the wound rotor, for any value of stator and rotor current I1 and I2 respectively, AE upon EF is equal to I2 square R2 upon I1 square R1 is equal to I2 upon R1 I2 upon I1. Here we know that I1 upon I2 is equal to K, which is the transformation ratio. Now put this value here, then AE upon EF is equal to R2 upon R1 into 1 upon K square. Now finally we get this IR2 dash upon R1, and it is the equivalent, it is a ratio of equivalent rotor resistance per phase by rotor resistance per phase. Now let us assume that motor is running and taking a current OL. The motor is running and taking a current OL. Then from this circle diagram, JK is equal to fixed losses, Jn is equal to stator copper losses, NL is equal to rotor input, Nm is equal to rotor copper loss, Ml is equal to rotor output, Lk is equal to total motor input. Now the various relation with various quantities, that is to calculate the motor input, root 3 VL Lk is equal to motor input, root 3 VL Jn is equal to root 3 VL Jn is equal to stator copper losses, root 3 VL Mk is equal to total loss, root 3 VL NL is equal to rotor input, root 3 VN Jk is fixed losses, root 3 VL Mn is equal to rotor copper losses, root 3 VL Ml is equal to mechanical output. Now all these quantities we can calculate from the circle diagram by measuring the distance between in point A, L and K, J and N, Mk. We can calculate all these quantities. Now we can easily calculate the efficiency. Efficiency is calculated by the ml by lk is equal to output upon input, which is the efficiency. Now mn upon nk is equal to rotor copper losses by rotor input, which is slip. ml upon l is equal to rotor output divided by rotor input is equal to 1 minus s is equal to n upon ns is equal to actual speed divided by synchronous speed. We can easily calculate the ratio of actual speed of synchronous speed. Now Lk upon OL is equal to power factor. Now it is clearly indicates that from the circle diagram we easily determine all these values. We easily determine all these values from the circle diagram. Now we are taking some numerical on circle diagram. We have a 3-phase 400 volt induction motor. Give the following test readings. From the no load test, it gives 400 volt and 1250 watt, and from the short circuit 150 volt, 4 kilowatt and 38 ampere. We have to draw this circle diagram from these results, and if the normal rating is 14.9 kilowatts, find from the circle diagram the full load value of current and the power factor and the slip. We have to calculate these parameters from the circle diagram. Now the cos phi 0 is equal to 1250 divided by root 3 400 into 9 is equal to 0.2004, and we calculate phi 0. It is we calculate from the formula P is equal to root 3 VI cos phi. Then similarly we calculate phi s. Phi s is equal to 4000 divided by root 3 into 150 into 38, which is equal to 0.405, and phi is equal to 66.1. And now we calculate the short circuit current with normal voltages, which is ISN is equal to 38 into 400 by 150 is equal to 101.3 ampere. Now power taken would be 4000 into 400 by 150 whole square is equal to 28440 watt. Now we draw this circle diagram from these results. First we draw the axis. First we draw the axis y and x. It is the axis y and it is x. Now we know that we have to calculate OO dash. For the OO dash, we have the OO dash represent I0, which is the value of 9 ampere, and if we take a scale 1 centimeter is equal to 5 ampere, then the vector OO dash is equal to 9 by 5 is equal to 1.8 centimeter. The length of the OO dash is 1.8 centimeter and drawn at the angle of phi 0. Now phi 0, which is 78.5. Now we calculate. The angle is from y-axis now, so we put a protractor. It is O. We have to calculate O dash. Then put a protractor here and 78.5. Here, and length of is 1.8 centimeter. Then here it is the point where our O dash is made. Now the second step is draw a parallel line to the x-axis. Now we draw a parallel line. Remember that if error of 1 mm or 2 mm will be there, the result will not accurate. There is definitely something wrong result we get. Now after this we draw OA, and the OA represent the ISN, which is 101.3 ampere. We calculated it previously. It measures 101.3 by 5 is equal to 20.26 centimeters and drawn at the angle of 66.1 degree. So again it is 78.5 degree. Now for ISN it is 66 here. So from here we have to calculate as an approx 26.5 15. Right now I am using 15 centimeter scale. It is better to use 30 centimeter scale to remove the all error. Here it is the point, sorry, here it is point A. I refocus it. It is point A. So in total distance between point O and A is 20.26 centimeter. Now join the point A and O dash. Now we got the point O dash and A. Now bisect this O dash A to find out the point C to draw a circle. Now okay, so we find out the point C. This C is the center of the circle, and from this point to this we draw a circle. This is D. Now previously I said that the point O dash and A are lie on the circle. We draw as per the values. The point O dash and A lies on the circle. Now this O dash A is the output line. Now draw a perpendicular from point A to x-axis. This is point B and this is F. Now AF represents 2000 28440 watt and measure 8.1 centimeter. If we measure it, it is as an approx 8.1 centimeter, exactly 8.1 centimeter. Hence power becomes 3510 watt. Now full load motor output is equal to 14.9 into 10 to the power 3 is equal to 14900 watt. As per calculator scale, O dash A should measure 4.25 centimeter. Now for locating the point P, BA is extended up to the point S and it is equal to 4.25 centimeter. Now we have to extend this up to 4.25 centimeter. This is point S. We are extending it. And now, and SP is drawn parallel to the OA dash. We draw a line SP which is parallel to O dash A. It is parallel to O dash A. Now we draw a line it cuts somewhere here, so we connect O dash and this point. Sorry, it cuts somewhere here, so we connect O dash and this point, and this point is P, and it is we calculate 66.1 and it is the phi. If we measure it, it is as an approx. We can measure it from the protector. It is 30 degree. It is 30 degree. So the line OP is 6 centimeter. If we measure it, it is 6 centimeter long. So OP is 6 centimeter. So total value of the line current is 6 into 5 is the scale, is 30 ampere, and phi is 30 degree. By measurement we measure it. Now power factor is cos 30 degree is equal to 0.886. Cos phi 0 is equal to PL upon OP is equal to 5.2 by 6 is equal to 0.865. Slip is equal to rotor copper losses divided by rotor input. Slip is equal to EK upon PK. We are not marking it here. For this we have to draw a parallel line from perpendicular line on OX axis from this point P when we do it, we have a one point is here, that is E, and one point is here, that is K, and here it is L. If we measure these values, so the length of EK is 0.3 and PK is 4.5, so the slip is 0.067. So we got all the values from the circle diagram.